Okay, so I'm very pleased to have Wenping Yin with us today. He did his PhD, his bachelor's in China at the Northwestern Polytechnic, and then he did his master's at Peking University, and he's now at, I'm going to call it the University of Munich. I'm going to offend some people with that. Working with Heinrich Schütz, and he's produced an amazing number of publications in the last 3 years, almost 20 papers, almost all in top conferences, mostly on the intersection between deep learning and natural language. And I think he's going to talk to us today about some even newer stuff that he's been working on. So let him take it away.
Okay, hello everyone. Thanks for your interest. Very nice to meet you. I'm Wenpeng. The talk today is neural question answering over large graphs. This is my research background in my PhD. So in the beginning, I did some embedded learning for different granularity of language, like words, phrases, sentences, and some documents. Then I focused on the text matching. So given two pieces of text, like two sentences, I try to identify the relation for them. So for example, the paraphrase identification, text entailment, and answer selection for multiple choice questions. And recently, I'm mostly interested in the neural question answering over large graphs. It's also the topic today. First, I show you some example. Maybe that's too small. Okay. The left example is where Justin Bieber born. The right example is where Jackson Bieber born. So you know there are different names. The left is Justin Bieber. The right is Jackson Bieber. So this is the Bing search engine result. The left side, you can find that the Bing search engine returns the answer, London. Here, that's the answer for the question. However, the right side basically cannot find the answer from the returns. Unfortunately. This is another question: which university in the same city with MSR Cambridge? I searched that before I come here. Actually, you can find the Bing. Basically, it can return the correct answer: University Cambridge. At the top two return. The Google seems doesn't work well for this question. But you can also find the result of Bing maybe mainly based on the keywords margin or some information retrieval. Okay, so it's very common that a user will ask such question when, for example, for me to come here, I will ask such questions. So in this application, we have some large graph which can store the facts of the word, for example, Freebase, YAGO, NELL. This is a small snippet of the Freebase, like the entity Justin Bieber. You can find it's a person and it's a male, and the place of birth is London. And it has a sibling with Jackson Bieber. It's also person male, and you can notice that Justin Bieber doesn't have a place of birth in this Freebase, so it's a kind of missing fact from the Freebase. So retrieving the answer from large graph for the question what university in the same city with MSR Cambridge, it requires basically 3 steps. First is topic entity recognition. Then this example, it should map the MSR Cambridge to the Microsoft Research Cambridge. The second step is some relation identification. For this example, it should be located in and inverse located in. Here, star means the inverse relation. The third one, of course, is some reasoning algorithms. That's why I organize my content of this talk is like this. On the top, it's a large graph. Then I introduce the pass query answering. Pass query means we use some topic entity from the Freebase and some relations in the Freebase, like what's the place of birth of Jackson Bieber. So Jackson Bieber and the place of birth are existed in the large graph. So that's pass query. So we want to ask where does the Jackson Bieber born. Then we extend the application to some factoid question answering. So the question are raw text. It can be single relation or it can be multiple relation questions. Now first we go to the pass query answering. We start by a more formal description of the knowledge graph. It's a fact connection, like entity I, entity J. They are connected by the relation, like a relation K here. A path in knowledge graph can be written like this. The head entity EH and the tail entity ET, they are connected by a path in the knowledge graph. At each step, it's a relation like a relation 1 and entity 1, so they are connected. The biggest problem of knowledge graph is the sparsity. For example, we don't know the place of birth for Jackson Bieber. That's a sparsity problem. So the representation learning for knowledge graph is to encode the knowledge graph elements, like entities and the relations, enabling the generalization to real facts. That's the goal of representation learning. Okay, so the task of path query answering can be defined like this. Our system wants to test some, to predict some unknown facts. For example, the place of birth of Jackson Bieber, and based on the known facts, the Jackson Bieber has sibling Justin Bieber, and Justin Bieber's place of birth in London, Canada. That's the known facts. So the system trains unknown facts, then predicts the unknown facts. That's the task of path query answering. Oh, sorry. Oh, yeah. I was also shocked for finding that. So, yeah, more formally given a head entity and a relation sequence, the task is to predict the tail entity. So we want to use it to solve the sparsity problem of the knowledge graph. Some related work. First is one-hop modeling. So the input is just one-hop fact in the knowledge graph, giving the head entity and one relation to predict the tail entity. The trans-E and the whole HOLE, they basically give a score function for the single fact. So you can find it basically give a score for each single fact. Of course, there are some other work for this. And encoding multi-hop passes. So given the relation sequence, relation 1 to relation T like that, some work either they add the relation embeddings, add them, or multiply the relation embedding, or use recurrent neural network to encode the relation sequence from like left to right, one by one, to generate an overall path repetition. Finally, usually they compose the head entity with the path representation to predict the tail entity. So that's usually the related work does. Here, composition function is very flexible. For example, you can sum up the embedding of them, or you can use other composition function, for example, recurrent neural network to compose the two inputs. So it's very flexible. Oh, sorry. Yeah.
Can you say something about the difference between repeatedly applying one modeling to do relation sequences and these other approaches?
Basically, this you can do the repeated application of trans-E. Trans-E is just like sum the head entity with the relation embedding. So if you continue to add more relations, that's this, right? The top one. If you continue to use it, that's this. Some other work, if it multiplies the head entity with the relation, and you multiply multiple relations, that's this. That's the most commonly used baseline for this. Yeah. Of course, there are some new baseline use the recurrent neural network to encode the relation passes. Yeah. Another question here?
Is whole composable in that sense?
You mean this one?
Yeah.
You mean if it's composable training?
It made this distinction. Some models are composable, like trans-E, whereas the repeated application of the one-hop modeling is the same as the whole thing.
That's a good question, actually. In that work, they didn't do any composition function. Actually, I tried to implement whole by composition training, but I didn't get a good performance. So it can be composed training, but maybe the performance, I don't know. Yeah. In theory, it's okay. Yeah. Okay. So the problems for this work is, the first is, for example, if you add the relation embeddings, but if you shuffle the order, the relation order, for example, the relation is a friend and a mother, but if you change the order, they will generate the same representation for the relation path. So that's problematic. And the second is a longer path, then less effective. The third one is entities and the relations are not equally well-tuned, so it cannot give you a high-quality vector space because in this method, there's no entities in the relation path. So you cannot expect they can give you a vector space for the entities and the relations. So our inspiration is that we notice the relations and the entities appear alternatively in the relation paths. And we want to model the paths of arbitrary lengths and to train both entities and relations to give a high quality vector space. Then we can use a vector space for other tasks. The third one is a launch graph element should have different influence to the prediction depends on the context. For example, if we want to compose the place of birth with the context symboling, very likely it can be the place of birth. But if the context is a father, that's less likely to get the place of birth. So different context will generate different representation. So a potential solution is gated recurrent neural network. So the gating mechanism can tell us how much information we should encode for the current input and how much information we should encode from the past history. Okay, this is our first sequence-to-sequence model for this task. We split our path into a relation sequence and an entity sequence. We first initialize the gated recurrent neural network by the head entity. Use head entity to initialize the hidden state. Then run the GRU on the relation sequence. Then predict the entity sequence at each step. So the red node is the error between the ground source entity and the predicted entity. So that's the error. Then we use the error to update the whole system. That's the first sequence-to-sequence model. So the benefit here is it can encode the entity sequence and the relation sequence in a single prediction chain. So it's very simple.
So the output entities, there's often multiple, right, for many of the relations, right? If you say child or something, right?
Yeah.
So then your sequence has just one choice from that set?
For training set, we have only one actually. Yeah.
Just one random or one whatever.
The data set was created by randomly choose one ground source.
Yeah. Okay, I see.
Okay, and but the issue is the head entity cannot give effective guidance for this prediction when the path is too long. For example, here, because the current neural network usually can only remember the latest input, so maybe it cannot remember the information from the beginning. So we try to modify the first architecture to the second architecture. We first zero initialize the gated recurrent neural network, then run it on the relation sequence. But we compose the head entity with each hidden state, hi here, to predict the entity. The benefit here is the head entity can participate in the prediction more directly and more effectively. However, we have met a new problem is because the GRU usually remembers the latest input, so maybe there's potential mismatch between the head entity and the current hidden state. For example, this hidden state HT maybe mainly remembers the RT, but the RT and the head entity are far from each other. So potentially there is a mismatch between the semantic between the head entity and the current hidden state. So our plan is, how about we use the latest predict entity, like EI-1, to make up the mismatch between the head entity and the current hidden state. So that's our third sequence-to-sequence model. Now you can find we compose the head entity with the previous predicted entity EI-1 with the current hidden state to predict the entity. So it combines the first architecture and the second architecture. Now we put them together to compare. The first difference is there is only one composition process in the first architecture. However, there are two composition processes in the second and the third architectures. You can find the first composition can be the GRU to encode the resolution path. The second is a composition function to compose the head entity with the current hidden state. So there are two composition processes in the second and the third architecture. Here I list the formula for the three systems. You can find the first one, it composes the previous predicted entity with the current resolution input to predict the entity. And the composition function is just GRU. The second, we compose the head entity with the current hidden state. And the hidden state is generated by another GRU. And the third one is similar with the second one, just we have another input EI-1. Okay.
Both the entities and the relations are represented by continuous vectors, right?
Yeah.
And how high dimensional are they?
In this work, I remember it's 200. Yeah. Okay. Some similarities. Entities and the relations are in different spaces. And the gate mechanism enables flexible composition between the entities and the relations based on the path context. We fine-tune entity and the relation embeddings at each step of the passes. So we want to generate a high-quality vector space. Now we show some experiments for it. First is our path example. Here you can find the blue ones are entities and the black ones are relations. So the institution and the inverse place of birth are relations. The last red one is the target entity or tail entity. This table shows us that.
One more question. So when you train these models, what is the loss being optimized?
There's a red node in my figure. Oh yeah, those red nodes are error between the ground truth in the past, ground truth entity in the past, with our predicted embedding. So
Squared error.
yeah, you can use a square loss or cosine similarity. Doesn't matter. You can use whatever similarity score, but we do some negative sampling. So for each ground truth entity, we have some randomly selected negative loads. So make the ground truth ranked higher than negative entities. Yeah. So the red nodes are error. Okay, in testing, we only predict the tail entity and neglect the intermediate entities. So we want to compare with some other work. This is the result for the path query answering. We compared with some baseline. The composed trans-E is the state of art for this task. We can find our system are always better than the state of art, especially the third one is the best. And we compared the different composition function. You can recall that we use it to compose the head entity and the current hidden state. The GRU is better than the add, because if you add the embedding of entity and the relation, that means they are treated equally. But GRU can learn which part is more important to this prediction.
Which data set?
This is actually, that's the same data set with one of your paper. By Gu, Kevin Gu, Kevin Gu, yeah, in Stanford person.
Is it WordNet?
No, this is Freebase.
Oh, this is Freebase.
Yeah, I noticed your paper worked on WordNet.
Okay.
Yeah, we can discuss more in our person meeting. Yeah. Now we go a step further. We expect our sequence-to-sequence model can model the long passes and can encode the order of the passes, and can generalize better by fully tuning the entity and the relation embeddings. However, is that true? So we try to draw the performance curve for different path lengths. In most cases, we found our system are better than the baseline trans-E. However, there is a surprising phenomenon here. We expect the curve should decrease smoothly, but here you can find the length 2 and the length 4, the performance are much lower than the other cases. So we found that the even length passes are harder than odd length passes. We did some error analysis. We found it's mainly due to the existence of a large number of inverse relations, and most inverse relations are 1-to-n relations. So that means we compute a Spearman correlation between the inverse relation percentages and the system performance. They are always above 0.9. That means the more inverse relations and the worse performance. Yeah.
You said that when you had a collection property, you picked one at random for training.
Yeah.
And at test time, do you assess it as correct if it's one of the
No,
collection or if it's one?
not the measure is not accuracy. It's a ranking. So we want to know the ground truth ranking higher as possible.
You still need a definition of ground truth. So are you still picking one at random, or are you saying that any of them is right?
Yeah, they are always random actually. The ground truth is one of the ground truths. Yes. In large base, there must be multiple ground truths for the path, but the dataset only provides one of them. So, yeah. So the measurement is like here, it's hits 10, so top 10, not accuracy.
So there might be actually correct entities above the ground truth
Yeah.
in the 1-to-n case.
Yeah. Yeah.
That's a
I guess the follow-on question.
problem of
Does that mean is that the reason why you're getting worse performance on even length paths?
Yeah, which is dataset, for example, for the past NELL, actually there are about 50% relations are inverse solution. That's the problem for here. So that means it's always will generate, it should be generate multiple ground source, but the dataset only have one ground source, so the performance is very low. So for example, if you have 1,000 ground source, but your ground source is only ranked like top 900, then the performance is not good.
Is this a problem with your evaluation measure or with your model?
I prefer to say that it's a problem with dataset. Yeah. Yeah.
But you change your evaluation metric even with the given data.
Yes, and that's a good point. Here we just want to compare with some other work. Yeah. Otherwise, we don't know if we get their improvement. Yeah, that's good comment. Yeah. Okay. So path query answering assumes the existence of precise entities and relations in the query. In real-world application, questions are raw text. So how do we do this case? We need to project the factoid question into the path queries. Then the definition of factoid question answering can be defined like this. The input is raw question text, and then project to the path query. For example, where Trump born? So it projects the $Trump born in. And the second example is of which university in the same city as MSR Cambridge. So it projects the Microsoft Research Cambridge and located in and inverse located in. You can find the first example is one relation questions, and the second one is multiple relation questions. So if we can first do the single relation question answering, because in reality, most relations are single relation question, or then we can do some step further to make some modification or improvements to handle the multiple relation question answering. So now we do the factoid question answering, and first look at the single relation question answering. This is some examples for this problem. The first question is, what American cartoonist is the creator of limping cod? So you can find the limping cod is the topic entity, and the creator is the relation in the question. The Freebase provide the Andy limping cod. You can find the Andy is missing in the question, and the character created by here is the paraphrase of the creator in the question, and the red one is the answer. The second question is what is active ingredient of BIF 0.05 solution? So BIF 0.05 solution is the topic entity, and the active ingredient is the solution. The Freebase provides BIF 0.05 injectable solution. So this word is also missing in the question. And this solution active ingredient mortise, you can find it basically the keywords of the question. Oh, sorry.
The first query is actually saying two constraints, right? It's saying there's an American cartoonist and creator of Lippincott. Right, they're American, they're a cartoonist, and they're a creator of Lippincott. So isn't the translation of the query really multiple simultaneous path queries? Or single-step queries, rather, right? Because there's 3 bits of information here about the answer.
Sorry, I guess I didn't get your point. Yeah.
Okay, so the question is what American cartoonist
Yeah.
is the creator of Lippincott?
Yeah.
So you have 3 bits of information. They're American, they're a cartoonist, and they're a creator of Lippincott. So you converted that into one query, essentially.
Actually, in question answering, we treat American cartoonist as some constraint. They're not entity and oscillations. For example, now we get some a list of answer candidates. We will check which one is American cartoonist. So it's a type constraint.
There isn't a nationality of or profession of relation.
Yeah, if the entity has the property for like American and he's a cartoonist, then definitely it will be ranked higher.
But it's not a query, right? KB fact is the fact contained in the knowledge base, right?
The query is the question. This
I'm just querying whether it's a single query.
You were saying, you were implying that the second line is a query to the knowledge base, which it is not.
I understand. I was extrapolating from the statement of the fact and the highlighting in the query.
So
So that's what the query was.
is it the case that in this data set, large portion of the questions are actually irrelevant answering the question? Is that the difficulty of this data set?
in this data set, you mean?
Because it seems like only the last bit of the question is useful in answering this question. You can almost ignore the fact that it's a cartoonist or the fact that he is an American.
You mean this part, right?
Could have just as well said who is the creator of.
So that's not the same query, right? Because if you had multiple characters called Lippincott, as there may well be in the world, like, who's the creator of Garfield, right? Okay, yeah, there's Garfield in literature, there's Garfield in cartooning. If you know that this is a cartoonist, it's going to help disambiguate. I guess my better question is, when you look at real English queries that people are typing, do they fit into single or multiple relation form, or are they more like this one, which is really like 3 simultaneous single-step relation?
Yeah, for zero questions, potentially there some difference. For example, maybe in this question they will have multiple entities. For example, what's the place of birth of Justin Bieber's brother, Jackson Bieber? So in this sentence, there are multiple entities. That's another challenge. And another problem could be the text is very noisy, so it's also hard to map to the facts. Of course, there's some very in open domain question. Yeah, you cannot imagine that the question always like this. It's very challenging. Yeah. And some relations maybe are unseen in the Freebase. That's also a problem. Okay, another question here. Okay. So we observed that the surface for matching between the entity candidate and the entity mentioned in the question provide very straightforward clue. for example, the BIF0.05 injectable solution in knowledge graph and the BIF0.05 solution in question, they are matched in surface form. So we can infer that they may refer to the same entity in the word, even though we don't know the semantic behind them. And the relation is mostly the paraphrase or and key phrase for the question pattern. Here, question pattern means we mask the topic entity in the question and only treat the remaining words as question pattern. And we found the convolutional neural network mostly outperforms the recurrent neural network in some key phrase, keywords-oriented text matching. Here, I want to advertise a little bit for my latest work, comparative study for CNN and RN in natural language processing. So in this work, we compared the CNN and RN in a broad list of natural language processing tasks, and we found in most keywords or key phrase oriented like sentiment classification and paraphrase identification, answer selection. In such kind of task, the convolutional neural network is always better. So that's why we use a convolutional neural network in this task to match the relation and the question pattern. Okay, given the input are Freebase fact, subject, relation, object, and the question mention pattern, recall that we split the question by the entity dimension, and the remaining part is the question pattern. We have two components for this CNN. The first is the character level convolutional neural network. It matches the subject and the mention on surface form. The second is the word level convolution to match the relation and the question pattern. Object in the Freebase fact is answer by default. There are two steps for this task because the input is a raw text. So first we need to do some entity linking. Then the entity linking will provide lots of facts. Then our system will select the best facts which match the question best. So we have two-step pipelines. For entity linking, usually we have two steps to implement it. The first is we can retrieve the entity candidates from the knowledge graph, then use them to detect the entity dimension in the question to say which part in the question is referring to the entity candidate. Or we can first detect the entity dimension in the question. For example, what's the place of birth of Justin Bieber? Then Justin Bieber is the topic entity. Then we use Justin Bieber to retrieve the entity candidates from the Freebase. So we can do this two steps in different order. We define its passive entity linker if we first detect the entity candidates from Freebase, then detect the entity dimension in the question, or we define it an active entity linker if we do it in inverse order. For passive entity linker, the input is question. We use each word to retrieve the knowledge graph. So each word, it means if the question is what is, blah, blah, we can also use what is each word to retrieve the Freebase. Because potentially maybe our entity in the Freebase is also what potentially, yeah. So this method will generate a list of entities, and we use some ranking to give a ranking list of entities. Then for each entity, we detect the entity dimension. For example, if what is our entity, that means the question, what is the entity dimension in the question? Then the remaining part is the question pattern. So we have a list of entities. That means we will have a list of entity mention and the question pattern. This method will produce more than one entity dimension and a question pattern pair. For the active entity linker, the input is still the question. We first train a biased model, CRF, to detect the topic entity. For example, we can detect the topic entity is Justin Bieber. Then on one side, we can use Justin Bieber to retrieve the knowledge graph to get a small group of entity candidates. On the other side, we can mask the Justin Bieber in the question and treat the remaining parts as question pattern. So this method will produce only one topic entity dimension and a question pattern for each question. So you can notice it can get rid of lot of noise entities and noise pairs here.
an example of what is a mention and what is a pattern?
Oh, mention is the topic mention. For example, what's the place of birth of Jackson Bieber? Then Jackson Bieber is the topic mention. Pattern is without the topic mention. So what is the place of birth of? That's pattern.
Oh, with the slot.
Yeah. We mask the topic entity. The remaining part is pattern. Yeah. Okay, now we do fact selection. Entity linker provides entity candidates, and the entity candidates provide the fact candidate. Then our system tries to find the best fact which matches the question. Where was Trump born best? This is our system for the example. What major cities does US Route 2 run through? And the tuple is US Route 2 major cities. The first column is the character level convolutional network. It matches the Freebase subject u.s.route2 with the entity dimension US Route 2. You can find that some characters are missing, mismatch between them. And the second column is a word network convolutional network. So the relation is major cities, and the question pattern is what major city does. This is the mask of the entity. So run through, you can find that the entity and the relation are mostly the keywords for this question. The third column is the convolutional convolutional network to learn any representation for any input. The contribution here is we use attention from the relation embedding here to guide the representation learning for the question pattern. We hope this part, major city, can contribute more to the question representation because we notice that there are basically keywords or paraphrase like that. So we want this part to contribute more in this representation. Then we can compare them more effectively. That's our motivation. Okay, so we propose attentive maxpooling in word network convolutional network. We call it AMP CN. The motivation is the relation is mostly the paraphrase or keywords of the relation pattern. However, the traditional maxpooling TMP treat all n-grams equally. So we hope our attentive maxpooling can make sure the n-gram which better match the relation can contribute more to the question representation. This is our implementation for the attentive maxpooling. On the top, it's a relation embedding. And the second block here is the n-gram embedding for the question. So each column is one n-gram embedding. Traditional maxpooling will extract the maximum value from each row. So here you can find the 0.75, 0.34. That's the traditional maxpooling. However, we want to make some n-gram can contribute more to the failure question representation. So we first compute some margin score between the relation embedding and each n-gram embedding. The margin score here, we call it attention value. You can find that the first n-gram has a similarity 0.97. The third one is 0.76. So you can find that there are the top two most related n-grams. So how could we make them to contribute more to the failure representation? We first normalize the attention value by making the maximum value as 1, the negative value as 0, and the other values divided by the maximum value. Then use them to multiply the original feature matrix to get a new feature matrix. Then we do maxpooling over this new feature matrix. That's attentive maxpooling. So now you can notice that the new features always mostly come from the first n-gram and the third n-gram. Okay. So yeah. Retention value is just any margin score between the relation embedding and each column. So each column is n-gram in the question. Yeah. Okay, now we show some results. First is the entity linking. We compare our passive and active entity linker to the state-of-art linker. Both perform better than the state-of-art baseline. We also report the contribution of three features in the entity ranking. A, B, C. A, B are some overlapping features. That means we prefer the candidates which have longer overlap with the question. The third one is position feature, because we notice that usually the topic entity appear close to the end of the question. For example, what's the place of birth of Jackson Bieber? So Jackson Bieber is close to the end of the question. That's why we have a position feature here. So you can notice that all of them contribute.
What's the maximum achievable score here?
Sorry, Mark?
What is the maximum achievable score, say a human?
Oh, by human beings.
Yeah.
It's Lincoln. No report of human performance for entity Lincoln. I guess ideally it should be 100, right?
Because presumably some of the sentences are genuinely ambiguous as to which entities
Yeah,
they're referring
but human beings, we can detect the relations around the entity to see if the entity is what we want, right? That means we can consider the surface as well as the surrounding semantic of the entity. So I guess in survey we can solve it by 100.
He said something like which musician was born in London, right?
Yeah. so in Freebase, that London entity should have maybe another relation to say it's Canada's London, not UK London. So we can, yeah. So each entity has some relation surrounded, and it has some properties surrounded. So
How does that help? Sorry, I don't understand. If the text is which musician was born in London, how is anyone going to get that right?
Yeah, for Jackson Bieber, for example, entity linking is just for the topic entity in the question, not for the answer set, right? For example, the question is...
The question is, what musician was born in London?
But entity linking map the Jackson Bieber into Freebase, not London from Freebase, right?
There's London, UK and London, Canada, and it's unclear which one is meant. It's not clear in the question. So I think the point is there are some questions where you can't do this entity linking with 100%.
For entity link, I think you cannot solve it. That's a task of our system. So our system will detect UK London is the correct answer or Canada London is the correct answer. Because in the Freebase, there's a low link between the Justin Bieber with the London, Canada. Our system will build the link for them.
I don't think when the linking happened first, prior to the fact selection.
If it exists, if it connects the Jackson Bieber and the London, Canada or London, UK, then the system will directly return the answer. No reasoning required, right? Yeah.
Maybe move on. I've got a chance to ask you more later.
Yeah. So this system assumes that there's a low link between the topic entity and the answer entity. That's why we try to solve the sparsity problem. If there is a link between the query topic, query entity, and the answer entity, we don't need any reasoning for it because the Freebase can give us answer directly, precisely.
I have another question. Is there a chance that entity that is not ranked at the top can be in the processing later, in the later stage of the processing?
Yeah,
or do you only take the top one here?
No. That's very risky. For example, here top one is only, for the passive is only a half, 56. This is only 63 or 73. So in our experience, we also tuning this to see how many top n, what's the number of n can give us best performance. Usually it's very risky to only choose the top one. It's risky. Yeah.
Just conscious of the time, you have 15 minutes left.
Okay. So now we report the performance for the single relation question answering. We compare our attentive maxpooling with the three baselines. The first is memory network. The second is some encoder-decoder by character level. The third one is the state-of-art performance. So the first block is based on the passive entity linker, and the second block is active entity linker. You can find in both cases, our convolutional neural network can generate better performance, and our attentive maxpooling is always more effective than the conventional maxpooling. Okay, for this task, this is the first convolutional neural network for this problem, and potentially it may hint that the fact ranking is more effective than the fact generation. Our effective retention mechanism in maxpooling, and we found the entity linking provides a bigger role in this task. So we released our entity linker and the result to the community for fair comparison. Now we try to make some improvements to handle the multi-relation question answering. Some new challenges here. The first is a question now can refer to multiple relations. For example, what's the occupation of Trump's daughter? So the first relation can be daughter, then the second should be occupation. The zero-shot relation detection, because in open domain questions, lots of relations may be unseen in the training set. And there are more noise passes because of now we consider multiple hole. Our inspiration is that could we detect the relations from the question directly? For example, what's the occupation of Trump's daughter? We can use entity linker to detect the dollar Trump. In the same time, we can detect the daughter and occupation based on the question directly. In this case, we can make sure the entity candidates and the relation candidates can improve each other. For example, if the entity linker provides an entity which doesn't have a daughter relation, that means it will be ranked lower than other candidates. And there are various numbers of relations. So this question has 2 relations. Maybe other relations will have 1, 3, 4 relations. So the best way is to relation names are in the sequence-to-sequence space we introduced in the first part, and the relation words in the word-to-vec spaces. So we try to combine the 2 spaces to alleviate the zero-shot problem. We try to handle this multi-relation question answering by improving the relation detection system. In the beginning, we assume that a raw entity linker gives us some raw entities. Then we do the relation detector based on the raw question and the connected relations. So it will give us the scored relations. This step can make sure to get rid of some unrelated relations. Then we use the scored relation to re-rank the entities. So this step, we can make sure the entities with more related relations will be ranked higher than the relation with less related entities. Now we use the entities to detect the relation question pattern. So this is a question pattern. So we mask the entities now and use the question pattern to detect the relations. Then we can get some new ranked relations. So you can find that the whole step is some ranked entities, ranked relations, and they improve each other. Finally, we combine the ranked entities and the re-ranked relations to get some ranked queries and use a top query to retrieve the large graph. This is our encoder-decoder for the relation detection. The given question is who lives in the same city with entity's mother. So it can generate the mother living and the inverse living here. You'll notice that the mother is a single word, and we use word-to-vec to initialize it. And the live-in has 2 words inside. We use word-to-vec to initialize live-in and in, and use sequence-to-sequence vector space to initialize the live-in. The same case with inverse live-in. So this is the relation detector. The big challenge for this is the training set. So we train this relation detector on the training set of these 2 datasets. Both provide the ground source entity and the relations behind it. And this entity relation detector gives a score for the relation and the entity pair. Now let's revisit the picture. you can find the key component of this task is the relation detector, and each part is just some ranking. So what we do is just tuning the hyperparameters in the ranking system. Now we report the performance for the relation detection. We compare with two state of art. The first is still the attentive maxpooling convolutional network. The input is the relation words. And the second is also by Microsoft research. It's by convolutional network. The input is the characteristic engram. We use relation names and relation words, and we get better performance. We also try to discard the relation names or relation words. We found both help and the relation words contribute more because it can alleviate the zero-shot problem better. This is the whole performance for the multi-relation question answering. The first baseline is still by Microsoft research. It's not a deep learning system, it's a dependence parsing system, STAGG. It was a state of art for the multi-relation question answering. The second is still our system, and now it's still the state of art for the single relation question answering. Our new system gets further improvement over the single relation question answer and get comparable performance in the multi-relation question answering. We also found the entity re-ranking and the entity type constraint is the help for this task. The summary for this talk, first we shoot the range graph and the path query answering. Then we extend the task to a factoid question answering. First is single relation question answering, then multi-relation question answering. Some problems or some challenges here. The first is one-to-n relations and inverse relations. I know some researchers are working on some Gaussian distribution for the relations. So maybe the tail relation are not one point in the space now, they are a region in the space. Potentially that's our solution for it. Oh, sorry. Second is word-based matching between the question and the relation is less effective in noise text, for example, in tweets or some random typo in the question. So word level matching is less effective. Now, a more popular method could be character level matching between them. The current datasets are not big enough to train our encoder-decoder relation detector pair. The limitations of large graph and the question. Non-large graphs don't have a common sense knowledge like usually women has longer hair than men. Some researchers are working on probabilistic large graphs or reasoning from multimodal resources. Maybe that's a good solution. And the second one is there are diverse form of questions like diagram and digits or code switching in the question. Limitation of deep neural networks. First, it requires large scale and data to train a good system. Second, now deep learning cannot compare, for example, 40 is smaller than 50, and it cannot count like how many persons in this room. So that's a limitation of deep learning. There are lots of other limitations. So my personal opinion is we should combine the deep learning with non-deep learning on rich form of knowledge. Finally, I want to thank my co-authors, my advisor Henry Schutz, and my colleague Yadola, and three researchers in IBM Watson, Mo, Bin, and Bowen. Okay, thanks to all you guys. Yeah.
In the path query part, in the first part of your talk, looked like the add versus GRU didn't make that much difference.
Add, right? GRU and add, right?
Right. So does that mean that the order that relations appear in the path doesn't matter so much?
It's here, right?
Right. So I guess you made a point that GRU is order sensitive, whereas add is not order sensitive.
Yeah, that's true in hits 10, the difference is big, right? I guess you mean in the mean rank.
Yeah,
Yeah.
mostly.
Yeah, that's true. Because in mean rank it's less sensitive to the position of the ground truth, because potentially in case you have multiple ground truths, you rank the 10 none, the mean rank is less sensitive. That's true for this dataset. This measurement is not that clear to show the difference.
In this data set,
Hmm.
what is distribution over query path lengths?
Distribution for the length? You mean? Oh, actually, when we draw this curve, we check the size of each path length. Roughly, they are equally distributed.
1, 2, 3, 4, and 5.
First, like each one is 20% like that, around, yeah. Yeah. Otherwise, this curve doesn't make sense if one size is too few. Yeah.
So you've shown sort of difference in headline numbers, like you get 3% more question answering or whatever. Have you looked at which kinds of questions that you get right that other systems have not?
I guess.
For example, in that more specifically in the GRU versus add, you look at which queries you're getting right when you were order sensitive versus weren't.
We didn't do the error search for past query answer, but we did some error analysis for the factoid questions. Usually, if the question like if it's asked some digits like what's the year, what's the time like this, then the performance is better. If it asks some entities, that's better. So it depends on the entity type actually. Yeah, for this test, usually they ask some real entities, but if you ask some why question, like why blah blah blah, it cannot be answered by a large graph. So. Yeah.